Welcome to today's lecture on energy balances and how to perform them. Basically, we will be looking at the objectives and procedures involved in performing energy balance calculations. In the previous lecture, we had looked at mechanical energy balances. From this point on, we will be focusing more on chemical processes where change in enthalpy and internal energy play a much huge role compared to kinetic energy and potential energy. So, we will be looking for these types of processes and performing energy balances on them. Before we start performing these calculations, we will have this introductory lecture where we will talk about the overall objective and procedures which are involved in calculating changes in internal energy and enthalpy. So, what are the objectives of performing energy balance calculations for chemical processes? The chemical processes are the ones where you have pressure, temperature, phase and composition are changing during the process happening. So, for this type of a process we might have to be calculating internal energy and enthalpy changes. So, we will be using changes in internal energy for closed systems and changes in enthalpy for open systems. So, to calculate these change in internal energy or enthalpy, we would not be able to do it when all things which I have mentioned are changing. If everything like temperature, pressure and phase are changing, we cannot use one simple equation to solve for all these values. Instead, what we can actually do is calculate change in internal energy or enthalpy for the following processes, where pressure changes at constant temperature and state of aggregation or phase, where temperature changes at constant pressure and phase, where phase changes at constant temperature and pressure, and when there are mixing of two liquids or dissolving of a gas or a solid in a liquid at constant temperature and pressure. So, these are the types of processes for which we can actually quantify or calculate changes in internal energy or enthalpy. So, the process would have to have two of the parameters to be a constant and only one of the parameters to be changing. For something like this to happen, it has to be a hypothetical case, because in real scenarios you would not have a step by step procedure where you would go from changing pressure first and then changing temperature. Usually processes are done in a way that both temperature and pressure will be changing simultaneously. So, in such scenarios, how do we actually calculate the change in internal energy and enthalpy? So, we will look at how the procedure for calculating these would be. The first step is you can actually understand that these values can be calculated for processes where all factors are changing, where both temperature, pressure and even phase is changing. You can actually calculate the total change in internal energy or enthalpy using the steps which I had given below. So, if you calculate the change in internal energy or enthalpy for these individual states, you can actually build a hypothetical process which can actually be brought together to define any process in the system. Why is this possible? Why are we able to do this? It is because the fact that these two properties are state properties and not path functions. This means that the change in enthalpy can be calculated for any path, and as long as the summation of the path represents the actual path, you would not have any problems with the numerical value you have obtained for the change in enthalpy. That is the beauty of using state functions, and we will be trying to exploit this property of enthalpy and internal energy to perform calculations which are feasible. So, how do we do this? We will be building a hypothetical process path between the initial and final states. We will explain that in greater detail with some examples, but what we basically do is we create a series of steps which are of the given types, where you have only temperature changing at constant pressure and phase, or where you have pressure changing at constant temperature and phase and so on. So, each of these steps will follow this rule, and we will have a series of steps so that the initial condition finally reaches the final condition through these smaller steps. The change in enthalpy for these individual steps are calculated, and the summation of the change in enthalpies for all the steps will give you the total change in enthalpy or internal energy for the true process which you are looking at. So, let us assume this process where solid cyclohexane at 0 degree Celsius and 1 atmosphere is converted to cyclohexane vapor at 200 degree Celsius and 3 atmospheres. What you see here is all three factors are changing. Your temperature is changing from 0 degree Celsius to 200 degree Celsius, pressure is changing from 1 atmosphere to 3 atmospheres, phase is changing from solid to vapor. So, what you actually have is all three things changing and most probably simultaneously. How do you calculate change in internal energy or enthalpy for such a process? If you had a table like a steam table, if you had a table for cyclohexane which gives you the internal energies and enthalpies in reference to a reference state, you can basically take these two conditions, identify what their internal energies or enthalpies are and find the difference, and you would be able to get the change in internal energy or enthalpy. However, no such table exists for cyclohexane. So, what do we do to solve it? That is where building a hypothetical path comes into play. So, how do we build this hypothetical path? So, what are the constraints which need to be followed? As I already mentioned, we would have to be able to calculate internal energy changes and enthalpy changes only when one of the three factors are changing: temperature, pressure or phase. So, we would have to make sure that each of the step only one of these three changes and the other two remain a constant. So, what we would have is a process where each step in the hypothetical path would have only temperature or pressure or phase changing, not more than one. So, the phase changes would also have to happen at temperatures where enthalpy associated with phase change is available for us from some table. This is usually available for melting point and boiling point at 1 atmospheres. So, the phase change itself would have to happen at the melting point and boiling point of cyclohexane. So, first thing to identify then is what are the melting points and boiling points of cyclohexane. At 1 atmosphere, the melting point for cyclohexane is 6.7 degree Celsius and boiling point is 80.7 degree Celsius. Now that we know these two values, we should verify if the specific enthalpy changes for the process of melting and vaporization are available in some handbooks. Usually these are available in handbooks given for data, so such as Perry's handbook, or even one of the prescribed textbooks has appendices which have these data. So, using these enthalpy values, we would be able to directly plug them in for the hypothetical path. So, the phase change steps would have to happen at 1 atmosphere and melting point of 6.7 and boiling point of 80.7. This means that when cyclohexane solid is getting converted to cyclohexane liquid, that has to happen at 1 atmosphere and 6.7 degree Celsius, and cyclohexane liquid to cyclohexane vapor has to happen at 1 atmosphere and 80.7 degree Celsius. So, the hypothetical path that you build would have to have these two steps. Now, let us see how we can construct this hypothetical path. So, we have been told that the overall process is solid cyclohexane at 0 degree Celsius 1 atmosphere going to vapor cyclohexane at 200 degree Celsius and 3 atmospheres, and we have also been given data that melting point for cyclohexane is 6.7 degree Celsius and boiling point for cyclohexane is 80.7 degree Celsius. Using this information, let us try to build the hypothetical path. So, the real true path is this, where you go from initial, which is solid 0 degree Celsius and 1 atmosphere. From here you go to vapor 200 degree Celsius and 3 atmosphere. So, this is the true path. Now, we are going to build a hypothetical path. So, we know that melting point is 6.7 degree Celsius. So, the change of phase from solid to liquid has to happen at that temperature. So, let us assume that the first step takes this initial phase to solid at 6.7 degree Celsius and 1 atmosphere. Here in this process what you have is only delta T, only temperature is changing, whereas pressure and phase have not changed. Phase is still a solid and pressure is still at 1 atmosphere. So, the next step, let it be the change in phase. So, at 6.7 degree Celsius 1 atmosphere, cyclohexane will start to melt. So, you would end up with liquid 6.7 degree Celsius 1 atmosphere as the next step of the process. So, from here So, in this process you only had change in phase, there is no change in temperature or pressure. So, from here you can actually heat the process up further, heat the system up further to reach liquid at 80.7 degrees Celsius and 1 atmosphere. So, here there is again only delta T, which is change in temperature, phase is still a solid and is still a liquid, and pressure is still at 1 atmosphere. So, from here we can have change in phase where it goes to vapor at 80.7 degrees Celsius and 1 atmosphere. So, this is delta phi, there is only change in phase here, temperature and pressure are remaining a constant, and from this we can go to the step where it is vapor at 200 degrees Celsius and 1 atmosphere. So, here you have only change in temperature, the vapor is being heated from 80.7 degrees Celsius to 200 degrees Celsius, and it is at a constant pressure of 1 atmosphere. So, from here you can reach the final step of the process, which is 200 degrees Celsius vapor at 3 atmospheres. So, here only pressure is changing and there is no change in phase or temperature. So, this is a hypothetical path which we have built. So, the one process step which is the true process has been built into step 1, 2, 3, 4, 5 and 6. So, instead of having one single path, we have 6 steps which describe the overall process. With these 6 steps we can actually calculate the change in enthalpies for each of the step. The first step is only change in temperature, so you would be able to use integral Cp dt. The second step is only change in phase, the value is directly available from the textbooks or any handbook. The third step is again just change in temperature, so again you can use integral Cp dt. The only important thing which you should note is for the first integral Cp dt you would have used the Cp for cyclohexane solid, and the second integral Cp dt which is for the process step 3 you would be using integral Cp dt with Cp of liquid cyclohexane. The third step is change in phase, which is vaporization of cyclohexane. So, you have the heat of vaporization again available from a textbook or handbook. The step after that, the fifth step is change in temperature, which is heating from 80 degrees Celsius to 200 degrees Celsius. Here you can calculate enthalpy as integral Cp dt. Here you will be using Cp of cyclohexane vapor, and the last step is change in phase, which is change in pressure. The change in pressure is from 1 atmosphere to 3 atmospheres. If you were to assume an ideal gas behavior, this particular change in pressure would not cause any change in enthalpy or internal energy. So, that would be 0. So, the summation of the enthalpies for each of these steps can actually be brought together to give you the total change in enthalpy for the overall process which has been described. So, this process which we followed is called as building a hypothetical path. So, I will give more tutorial problems and exercise problems which will help you build this hypothetical path. This is not the only hypothetical path you can build. For the same process you might be able to build different hypothetical paths depending on what information is available to you. So, here I had given you that the information for enthalpy was available to you at specific boiling points and melting points, and based on that you had built this hypothetical path. If the data given is different, you might be able to build a completely different hypothetical path and you will be able to arrive at the same answers. Now that we are familiar with building hypothetical paths, we will look at the overall procedure which needs to be followed for performing any energy balance calculations. So, we did something like this when we prepared material balance calculations also. We looked at an overall process. So, we will look at this overall process and we will try to stick to this process and procedure whenever we perform any energy balance calculation, so that we get completely familiarized and it becomes second nature for us to follow this procedure while we perform energy balances. So, this is meticulously prepared so that we can avoid any errors. So, please try to follow the procedure strictly while you perform these calculations in any exam or even when you are just performing these calculations for assignments and practice. Energy balance calculations themselves are a lot harder or lot trickier than material balance calculations, because for performing energy balances you should need to have completed material balances. In some cases, especially in exam settings and in assignments which I hand out, you might end up having material balances already solved for you. However, in real life scenarios, material balances might not be solved for you. So, if you are going to design a plant and you need to understand the energy requirements, you first need to complete all the material balances which are associated with it, so that you know how much energy would be required for each of the process. So, because of this, the first step for any energy balance calculation which you would be doing is to perform all the required material balance calculations, so that you have information about all the flow rates. If you remember, you had the specific enthalpy calculations which I described earlier. So, from the specific enthalpy you would have to calculate total enthalpy changes. Similarly, if you are having a closed system, you would have to calculate total internal energy changes. So, this can be done only when the mass flow rates or masses or moles or molar flow rates are known. So, this means understanding and calculating all the material balances is crucial. So, the first step for any energy balance problem is to perform material balances. Even if I skip them while I am performing energy balances here, it is probably because the material balances are not required, as they have already been given to us. In real life that would not be the case. Having said all this, let us go on to the next step. The next step is to identify the type of a system which you are working with. You need to know whether it is an open system or a closed system, and you need to write down the appropriate form of energy balance, either it is open or closed system, and you would have to delete any zero term, so or negligible term. So, if you have no change in velocity, you would assume kinetic energy to be 0. If there is no change in position, you would assume change in potential energy to be 0. If there are no moving parts, you would assume shaft work to be 0. If the process is adiabatic, then you would have Q or heat transfer to be 0. If you have such a system, you would have to make sure every factor is cancelled before you perform further calculations. You would have to choose something called a reference state. While we performed material balances, we always used a basis. So, based on the basis we performed all the calculations. When we perform energy balances, it is important to choose a reference state, because if you remember, we mentioned this in earlier lectures, enthalpy and internal energy changes can be measured. However, we cannot measure the absolute values. So, this means whatever calculations you are performing would have to be in reference to a reference condition. So, the reference state will be defined as a particular phase, temperature and pressure. You can actually choose different reference states for different components in the system. If you have a 4 component system, all 4 components can actually have 4 different reference states, and you can choose the data reference states based on how you are going to perform the calculations. If data is available from a table, then the reference state used in the table might be the most appropriate reference state to use. For example, if you have steam as one of the components in the process, you would be smart to use steam tables rather than perform calculations every single time. So, to use steam tables, you would have to use the appropriate reference state which has been used in the steam tables you are using. If you were to use the steam tables from Felder-Rousseau, you would use water liquid at triple point as the reference state. So, if you are not using data from a table, then you can use either the inlet conditions or outlet conditions. This way you can actually lessen the number of calculations you might have to perform. Once you have the reference states, you start looking at the system which is a closed system or an open system. If the system is a closed system, you would basically construct a table which has columns for initial and final amounts of each species, and for constant volume systems you will be writing down specific internal energy changes relative to the chosen reference state, and for constant pressure systems you will be writing down specific enthalpy changes instead of internal energy changes. For an open system, you will again construct a similar table. Instead of initial and final condition, you will have inlet and outlet conditions, and you will be calculating changes in specific enthalpies. The first important thing which we need to do is, this table has to be complete. There cannot be any unknowns. So, we need to calculate all the required specific internal energies and specific enthalpies and enter them into this table. With this, the table will have all the data required for performing energy balance calculations. Once you have this, you would have to calculate the total change in internal energy or enthalpy. So, this would be the formula you would use. Total change in internal energy would be sigma of the internal energy changes associated with individual components of the final condition minus the similar thing for initial condition, which is sigma final Ni ui cap minus sigma initial Ni ui cap. It could also be in terms of Mi ui cap instead of Ni ui cap, depending on the units for the internal energy which you have calculated. If the specific internal energy you calculated is joules per mole, then you would use number of moles of each component. If the units for specific internal energy is joules per kilogram, you would use masses instead of moles. Similarly, you can calculate the total change in enthalpy as sigma of the outlet streams, which would be Ni dot Hi cap, minus sigma for the inlet streams, which is Ni dot Hi cap. So, here your difference which you are calculating is between the outlet and the inlet instead of final and initial. So, you might also have to use mass just like how you did for internal energy, in case the enthalpy specific enthalpy values are given as kilojoules per kilogram instead of kilojoules per mole. So, if it is kilojoules per mole, you would use molar flow rates, and if it is joules per kilogram or gram, then you will use mass flow rates. So, once you do all this, your calculations are not complete, because you have only calculated total change in enthalpy. You still have to calculate if there is any work done by the system or on the system, if there is any change in potential energy or kinetic energy which you have not dropped from the general energy balance equation. The equation which you wrote down, some of the terms would have gone to 0, but some might still remain. You need to make sure that you calculate the numerical values for all the terms that still remain. Once you calculate all these values, you would plug them into the equation which you had, and you would be able to solve for the unknown. The unknown could most probably be Q, which is the heat which needs to be transferred. So, or Q dot in case of open systems. So, what the equation used would be is, for closed system it is Q minus W equals delta U plus delta Ek plus delta Ep, and for open systems it will be Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. So, with this you would be completing your general energy balance calculations. To fully understand the procedure which we described just now, I will show an example problem. For this problem, we will actually not be performing any numerical calculations. We will only follow the steps which we had to go through. So, here is the problem. Acetone is partially condensed out of a gas stream containing 66.9 mole percent acetone vapor, and the balance is nitrogen. Process specifications and material balance calculations lead to the flow chart shown below. The process operates at steady state. Calculate the required cooling rate. So, you have been given a flow chart and you have been asked to calculate the rate of cooling, which is Q dot. So, you have also been given all the flow rates. The material balances are already done for you. So, now let us see how we would go about approaching such a problem. So, again I am not going to be performing any numerical calculations here. I only want to emphasize the procedure which should be followed. So, please try to follow this procedure clearly. I will try to use the same procedure for every energy balance calculation which we perform throughout this course. What did we say was the first step for any energy balance calculation? Material balances. Here, do we need to perform any material balances? The information given to us is 100 moles per second coming in, 36.45 moles per second leaving in one stream, and 63.55 moles leaving in another stream, and we also have the composition of each of these streams given to us. This means all the material balances have been done. So, the first step is material balances, which has already been done for us. The next step is to identify what type of a system it is. So, what is this system? Is this an open system or a closed system? We see that there is a molar flow rate which is coming in and molar flow rates for the streams leaving, which means it is an open system. So, the appropriate equation for an open system would be Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. So, in this equation which terms would go to 0? There are no moving parts in this system, it is only a condenser. So, shaft work will be 0. You also have no change in velocity which has been given to you. So, kinetic energy change will go to 0. There is no change in position which has been given to us. So, we can assume potential energy changes are also negligible or close to 0. So, the equation simplifies to Q dot equals delta H dot, and we already know that delta H dot for an open system is basically sigma of outlet Ni dot delta Hi cap minus sigma of inlet Ni dot delta Hi cap. Now, we need to calculate this so that we can get Q dot. So, that is what has been asked for. So, the next step is to identify reference states. So, what would be the reference states we can use? As I had mentioned earlier, for every distinct chemical component in the system we can use a different reference state. In this particular system we have two components, one is acetone and the second is nitrogen. So, we can actually choose two different reference states for acetone and nitrogen. Let us see what would decide what reference states to use. For acetone we do not have any tables which we can look up, which means we would have to use either the inlet or the outlet conditions as our reference states. With that in mind, I have identified the reference states for acetone as liquid 20 degrees Celsius 5 atmospheres. So, this would be the reference state of the outlet stream of acetone liquid leaving the condenser. So, I have used this as the reference state. So, the change in specific enthalpy for the liquid stream leaving acetone with respect to the reference state would be 0. So, that would be one lesser calculation for me. So, other reference state I would have to choose is for nitrogen. For nitrogen there are some tables which are available. So, in Felder-Rousseau there is a table which is available in appendix B which gives values for enthalpy changes with respect to a particular reference state. Keeping that in mind, I have used the reference state that has been used in the table given in Felder-Rousseau. So, the table uses a reference state of gas 25 degrees Celsius and 1 atmosphere. So, with this I would be able to use values directly from the table rather than perform the calculations myself. This will make my life a lot easier when I perform calculations to measure or quantify specific enthalpy changes. The next step is to construct an inlet outlet enthalpy table. So, let us look at how the table should be constructed. We first have to write down all the substances or components which are there. So, here we will write down the phase distinct components separately. Acetone vapor will be written down as one component and acetone liquid would be written down as another component, so that we can explicitly understand and account for phase changes. Nitrogen would be another component. So, now you have molar flow rates N dot in which is in terms of moles per second, and you also have to calculate the specific enthalpy changes in terms of kilojoules per mole, and you have outlet streams which is N dot out in moles per second and H cap out in kilojoules per mole. So, we should not forget that the reference conditions which are used are acetone liquid 20 degrees Celsius 5 atmospheres and nitrogen gas 25 degrees Celsius 1 atmosphere. So, this is the table we would be looking to use. So, our goal is to fill this table. So, the molar flow rate for acetone which is entering is 0.669 times 100. So, which is 66.9, and you do not have any acetone liquid entering, nitrogen would be 0.331 times 100, which is 33.1. So, similarly the outlet streams, you have 36.45 moles of acetone nitrogen vapor mixture leaving. So, acetone vapor leaving would be 0.092 times 36.45, which is roughly 3.35. Acetone liquid leaving is only through this stream, and we know the number of moles is 63.55. Nitrogen is not changing phase or going through any reaction here. So, whatever is entering would be leaving. So, that is 33.1 moles of nitrogen leaving. So, amongst these components we now have to calculate specific enthalpies for terms which do not go to 0. Acetone vapor compared to acetone liquid at 20 degrees Celsius and 5 atmospheres would have a specific enthalpy term. So, this term would be labeled as H1 cap. This does not have any inlet, so let us not worry about that term. Nitrogen is coming in at 65 degrees Celsius and 1 atmosphere, and the reference we have used is gas 25 degrees Celsius 1 atmosphere. So, there is a change in temperature, which means this would also have an associated enthalpy with it. Now, for acetone vapor which is leaving through the exit stream, it is leaving at 20 degrees Celsius and 5 atmosphere. However, it is a vapor at 20 degrees Celsius and 5 atmospheres, not a liquid at 20 degrees Celsius and 5 atmospheres, which means this would also have a different enthalpy than the reference state. So, we would have to calculate this H3 cap. So, the acetone liquid which is leaving the stream as the product is the reference state which we have used, which means this would have an enthalpy value of 0. The specific enthalpy in this table would be 0. Now, for nitrogen, it is leaving as 20 degrees Celsius and 5 atmospheres compared to the reference which is 25 degrees Celsius and 1 atmosphere. This means that there would be an enthalpy change here also. So, there are 4 different specific enthalpies which need to be calculated to complete this table. Okay. Let us try to calculate one enthalpy. So, as I already said, I am not going to be looking at the numerical calculations, I am only going to try to show how the calculations have to be done. The specific enthalpy change H1 cap which we are trying to calculate is actually the change in H cap for the process where acetone from the reference state, which is acetone liquid at 20 degrees Celsius and 5 atmosphere, reaches acetone vapor at 65 degrees Celsius and 5 atmosphere, which is the condition of the inlet acetone. So, for this process we now need to build a hypothetical path, because here you have phase and temperature changing. So, we would have to build a hypothetical path in a way that we would be able to calculate individual enthalpies. As I already mentioned, you can build a hypothetical path for a process having phase change only when you know the enthalpy of phase change at some point. So, for which is usually available for boiling point or for melting point. So, here you have liquid getting converted to vapor. So, we need to identify the boiling point of acetone, and one of the steps where the phase change happens has to happen at boiling point at 1 atmosphere. So, this means the hypothetical path would also have to include pressure changes, so that the process would have the step where phase change happens at boiling point and 1 atmosphere. So, the boiling point for acetone is 56 degrees Celsius. So, this can be looked up any table. So, once you have this, we will now have to build a hypothetical path. So, what we have is acetone liquid 20 degrees Celsius 5 atmospheres going to acetone vapor 65 degrees Celsius 5 atmospheres. So, this is the true path. Now, we need to build the hypothetical path. So, there are many ways you can build the hypothetical path. So, the process which I have chosen is what I am describing here. So, the first step is to reduce the pressure. Here you have delta P, go to 1 atmosphere. Here you would have liquid 20 degrees Celsius 1 atmosphere. So, pressure change has happened. The next step is to increase the temperature so that it reaches its boiling point. So, here it goes to liquid at boiling point, which is 56 degrees Celsius and 1 atmosphere, and from this it gets converted where the phase change happens. So, you have delta phi where only phase change happens to get to vapor at 56 degrees Celsius and 1 atmosphere. So, from here you have to increase the temperature to vapor at 65 degrees Celsius and 1 atmosphere. So, here you have only delta T, and the last step is only delta P reaching acetone vapor at 65 degrees Celsius and 5 atmospheres. Now, we have built a hypothetical path where there are 1, 2, 3, 4 and 5 steps. So, the first step is delta P, second step is delta T, third step is delta phi or phase change, fourth step is again delta T, fifth step is delta P. So, we will call the enthalpy changes associated with each of these steps as H1, H2, H3, H4 and H5. So, I have just labeled it as H1, H2, H3, H4, H5. Please do not confuse it with the H1s and H2s I have used in the table. So, the total enthalpy change, which is H1 cap, would be equal to the summation of these H1s, H1 plus H2 plus H3 plus H4 plus H5. So, we already know that H5 will be 0 because it is a gas where there is a very small amount of pressure change. Assuming ideal gas behavior, this would not matter. So, the equation simplifies to change in enthalpy for the 4 steps which are there. The first step is there is a change in pressure. The enthalpy change for the first step H1 would be equal to V cap delta P. It is a change in pressure for a liquid, so it would be V cap delta P. The second step is change in temperature, which would be integral Cp dt, where you would use Cp of liquid because the component is still liquid. The third step is where phase change is happening. So, you would look up the heat of vaporization from the tables. The fourth step is where you have again change in temperature, it will be Cp dt again, where you will use the Cp for acetone vapor. So, now the summation of these 4 things together will give you H1 cap, which is equal to H1 plus H2 plus H3 plus H4. Now that you have H1 cap, you have filled one value in your table. So, the table which you had, this value H1 has now been calculated. Similarly, you might have to perform calculations for H2 cap, H3 cap and H4 cap. Once you have all these values, your table is complete. So, now that you have completed the table, you would calculate delta H dot as sigma of outlet Ni dot Hi cap minus sigma of inlet Ni dot Hi cap. So, this will give you your change in enthalpy. So, substituting it back into the equation we had, which is Q dot equals delta H dot. So, this is the energy balance equation we came up with after we cancelled all the 0 terms, and we end up with calculating the value for Q dot using this simple equation. So, this is the overall procedure for performing calculations to get energy balances done. As you saw, the calculations are not easy and straightforward. There are many chances of making errors. So, please follow the procedure which I described here strictly and meticulously, so that you can minimize any chance of errors. With that, thank you and see you in the next lecture.